Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool Cloud, a cloud-based solution for bore field calculations. And today is the third part in our series about hybrid systems. If you recall, 2 weeks ago we started this series talking about hybrid systems and geothermal potential. Now, if you have not watched the previous videos in this series, please do so because they introduce important concepts that you will need in today's video. So to recap, the first part talked about what are hybrid systems. And we said that hybrid systems are combinations of technologies, a ground source heat pump with, for example, an air source heat pump, that together can heat or cool your building. So it's a combination of technologies. And on the other hand, we talked about geothermal potential. And we've said that a bore field can have either no geothermal potential, or it can have geothermal potential for power or for energy. And in the second part of this series, we explore that geothermal potential a little bit further. And we really got into the different methodologies that are implemented into GHEtool Cloud. We've said that, well, depending on the geothermal potential of your system, you can either design a hybrid system with a bore field to deliver you a maximum power, or you can use it to deliver you a maximum amount of energy. Based on two different methodologies, you will also get another result. And the final choice between optimizing for power or optimizing for energy was dependent on your economic parameters, investment cost, operational cost, etc. So in today's video, we will be going more practical and we will actually dive into GHEtool Cloud and we will go over a practical example, a real-life case, on how you can use GHEtool Cloud to design a hybrid system. Today we will be still talking about the thermal side, so to speak, and in a part 4 of this series we will extrapolate the results we get today to also a total cost of ownership analysis and some more economic parameters. But since that really depends on the country you're in, the prices of drilling and geothermal heat pumps, etc., it is a little bit decoupled from the optimization with GHEtool itself, which is the main focus of today. So the building we will be discussing is a multi-utility building. And the figure you see here is just an illustration. The case is real, but it's anonymized. So we have a building which has 536 kilowatts in heating power with 643 megawatt hours per year of energy demand. And in cooling, we have a higher peak of 676 kilowatts, but a lower yearly demand of 267 megawatt hours per year. And we know that if we want to heat and cool our building in a 100% geothermal energy way, that we would need 130 boreholes. But the problem is that in this case, there is only limited space and we can only drill 90 boreholes. So a 10 by 9 bore field. So the question is, how can we design a hybrid system which, together with this bore field, with this geothermal system, can heat and cool our building? And we can use GHEtool for that. So now let's jump over to GHEtool Cloud and get to work on this project. So now we're in GHEtool Cloud. I've created a new project with the name of hybrid system and we're ready to get started. First, what we're going to use is this optimise load profile method. In case you have a crown next to this method, it means that your current license does not include this hybridization methodology. If you want to use it for a particular project, you can upgrade that one project to a higher license, or you can check out the optimization license if you think this method will be useful for multiple projects. It's all over on our website and you can upgrade in your account dashboard. So let's go ahead and click on the optimize load profile. We're going to work with a simulation period of 40 years. It does not really matter that much, but I always try to use a 40-year simulation period, as it's also the standard by the BREEAM Institute or certification. Where we'll start by optimizing the power of the system, because then we know which power we can always get from the ground, and it's a good starting point to then move towards an energy optimization and see, given a specific borefield design, how much energy we can actually exchange with the ground. So that's for the general tab. If we move over to our ground tab, for this particular project, we're going to use a conductivity of 1.9 watts per meter Kelvin. Of course, this is very dependent on your project. If you want to create or follow along with what I'm doing here, all the parameters as also the results are linked over in our article. For the bore fields, as said before, we have the possibility to have a 10 by 9 grid of 6 by 6 meters in spacing. And for the borehole depth, we will use 150 meters with a buried depth of 0.7 meters. So this is the starting point, and we will check which geothermal share we can get with this bore field. Over in the borehole to resistance tab, we will work with the default values of GHEtool Cloud. And then in our thermal demand, we see that all the information is disabled because we need to upload a CSV file with our hourly demand. So let's go ahead and do that. Import this load profile and we're good to go. So now I will press calculate scenario and I see you when we get the results. So here we are. Sometimes, depending on the specific parameters you entered, your load profile or your borefield design, it can take a couple of minutes, but in the end we will end up with this result. So we have a lot of things to interpret here. First of all, we have our numerical results, as we know before, with a specific geothermal imbalance, as you can also see on the figure on the right. And we see that our borefield is indeed limited by both the maximum and the minimum temperature, so it has no more potential for power. It only has some potential left for energy. What can we also see? That when we look at our power and energy distribution, that around 3/4 of our total energy demand can be fulfilled with this geothermal system. So for our cooling, we have 26% of our total power demand can be delivered by the borefield, which is around 180 kilowatts. For the geothermal heating, we have 264 kilowatts of power that we need to install, and the other 54% of our total 570 kilowatts will be delivered by our other system. We also have here our load duration curve, where we can see that we have indeed a large area that is hedged, so that is the energy that we get from our geothermal bore field. So this is already an interesting starting point. With our 90 boreholes of 150 meters, we can get almost or a little bit over 75% of geothermal share in both heating and cooling. But let's see if we can optimize it somewhat further. So first of all, I will rename this scenario to optimize power, and I will just say 10/9. Perhaps what we can do is say, well, instead of installing a bore field which has a dimension of 10/9, perhaps we can make a 9/9 and see what the difference in results is. So if we duplicate the scenario and we say, well, now use a 9/9. So we rename the scenario. We go over to a bore field and we now say, well, it's a 9/9 bore field, and we optimize it again. We can see how the result changes. So whenever you're designing a hybrid system, you're always trying to find the optimum between the amount of boreholes you need to drill versus the geothermal share you can get. So with the 10/9, we saw that we were able to get 75% of geothermal share in both heating and cooling. If we, it's done calculating, go to 81 boreholes, we see that it's almost the same, let's say. So we have here 73% of geothermal heating and 74 in cooling. And in our previous scenario, it was 78 and 77.6. So it's almost the same, let's say, and we decreased the number of boreholes by 10%, which is a big saving in investment cost for almost no change in operational expenses, let's say. So perhaps we can duplicate it again and try, for example, a 9/8 bore field, and let's see what that gives us as a result. So we change the dimensions again and we recalculate the bore fields. And what you typically see is that when you keep doing this, after a specific moment, there will be a significant change in geothermal share you get. When you calculate it economically, it will no longer make sense to make the bore field smaller, because your geothermal share or your geothermal system will be way too small to be economically feasible in your total system. So when we do this, we see that our share is dropped to 68% in heating here and to 70% there. So if we compare it to the previous scenario, we can see there is a significant drop there. So if we make the bore field a little bit smaller, in this case we remove 9 more boreholes, we see that the geothermal share we get of the system is becoming significantly less. So in my opinion, when I see this in practice, I say, okay, let's, for example, stick with the 9/9. It seems to be almost as good as the 10/9, which is the optimal situation I can get from an energy perspective. But the 9/8, the geothermal share is too low, in my opinion, in this case. So this was for the optimization for power. So if we, for example, say, well, with this 9/9, if we duplicate the scenario, we're now going to optimize it for energy. So let's call this scenario optimize energy 9x9. We rename it. We go to our general tab and now we say, well, optimize it for energy. And if we now calculate it, it will figure out how much extra power we can install in order to access this energy potential of this bore field. So we see that this, when we optimize for power, there is still some geothermal potential for energy left in both heating and cooling. And by now optimizing it for energy, we will try to work that away. So once it's done, we end up with this figure. So first of all, I want to draw the attention to the temperature profile, where we now see that the potential for energy is totally filled. So we can see that we reach the temperature limits in every month of the simulation period. So what this algorithm did, it installs extra geothermal power and it used it so to get the most energy out of the ground over the whole simulation period. And that you can see here. So with the same bore field as before, we now get up to 83.6% of the energy demand in heating and 92% of the energy demand in cooling. So if you compare it again to our optimized power, there it was only 73% and 74%. But we had 160 kilowatts and 224 kilowatts in heating and cooling power geothermally. And now we have 342 and 509 kilowatts. So this is an important finding. Namely, we have, with this 341 kilowatts in cooling, we have 40% of the total installed power, that is geothermal, but the sum of both powers is more than our building demand. So that's an important difference between the optimized power and the optimized energy, is that when you optimize for energy, you will over-invest in one way, you will install too much power in order to get most out of your bore field, so to try to minimize the geothermal potential for energy. And for geothermal cooling, this is typically not that big of a problem, because in this case it's passive cooling. We set in the general tab, we used 70 degrees Celsius, which in the region of Belgium is typically a value for below which we can use passive cooling. So it's just a heat exchanger, which is not that costly. And by installing a bigger heat exchanger, we can get up to 92% of the energy demand in cooling. For heating, it's another story. Here we install 509 kilowatts of ground source heat pumps and another 280 kilowatts of our hybrid system. If we compare that to our optimized power solution, there we had 224 kilowatts in geothermal heating and 300 kilowatts in our hybrid solution. So the amount of power we have installed when we optimize for energy is way, way bigger in order to get up to this 83% of geothermal share. So that's something we're going to take a closer look at in our next scenario. But first, I would like to draw the attention to the geothermal distribution graph, which is perhaps something new for you. So since we optimize for energy, and as you can see in the figure below, every year we can extract a different amount of heat and cold from the ground. So in the first years, the ground is warmer, so we can extract more heat from the ground. But year after year, due to the imbalance, the ground cools down and we can cool more with the ground. So since every year is different, we needed a graph to show this to you as a user. And this is what the geothermal contribution graph looks like. So what you see here is in every year, you see the heat and cooling peak power and also the base load in both heating and cooling. And as you can see in the first year, there is a high heating power and a high heating base load, and year after year this decreases, and the peak power always decreases faster than our base load. And for the cooling, it increases year after year after year. So that's important to see that in the end it levels out. As you can also see on the temperature profile, it more or less stabilizes. But in the beginning, there is a big difference between the power you can exchange with the ground between the first and the last year of the simulation period. And on average, so the yearly average energy you exchange in heating and cooling is exactly what's shown here on the power and energy distribution. So if we say that 83% of the total heating demand of our building can be met with our geothermal system, it means that over the 40 years, on the figure on the right, we will get this 583 megawatt hours of energy in heating. So let's think a little bit how we can further optimize this, because although we're not doing economic evaluations at the moment, we can see that the difference between having 509 kilowatts of geothermal heating installed versus 224 kilowatts, it's a big difference. It's a very big investment cost that we need to do there. And we see that when we have 224 kilowatts in the optimized power, we already have 73% of the geothermal heating and cooling. So if we say, well, let's duplicate the scenario. Let's keep it that way. If we move over to our general tab, we can say that we have to limit the geothermal power. So for cooling, it was not that important. So let's set it back to 670 because it was our just a heat exchanger. But for heating, we can say, well, we do not want the full 509 kilowatts because that's way too expensive. But let's see if we, for example, install only 350 kilowatts. So limit your optimization to use only 350 kilowatts in heating. Now, what will this do? It will, first of all, make sure that the power will not go over 350 kilowatt installed, so you will always have a little bit of geothermal heating potential that is untouched. So it's not the optimal case in a certain sense, but it is most often the more economic situation. And this is what we end up with. So first, if you take a look at the temperature profile, we see that in comparison to the previous scenario, where we reached the minimum temperature also in the first year, we now have a little bit of energy potential left in this first year. And that's because we only install now 350 kilowatts of geothermal heating and no longer 509. But if we look at it from an energy perspective, we have now 83.4%, whereas before we have 83.6%. So by removing 150 kilowatts of installed geothermal heating, we have nearly lost anything. So this is a really interesting thing and sensitivity when you do this type of simulations, that you can actually decrease the power, the optimal power you can get from the ground to get a more economic situation, whereby you do not change really the geothermal share of your system. And you can also see that in the geothermal contribution graph. So in the first years, it's constant now. So in the last simulation, it dropped off from year 1, and because in year 2 there was already some imbalance, so a little bit of the installed power couldn't be used already in the second year. But here, since we only reach a temperature limit, I think here in January of the 4th year, the first years we use our installed power to the fullest. So what we can even do now, if we call the scenario not copy but 350 kilowatts, is we can try to go even lower and to say, well, instead of 350 kilowatts, let's see what it gives us when we go to 250 kilowatts, for example. So therefore we go back to our general tab, and we now said, well, limit the heating power to 250 kilowatts. And here we are. And what we can see now, if we limit it to 250 kilowatts, we get 78% of geothermal heating. And it seems like it's constant through the whole simulation period, which is interesting because now we see that we have no geothermal potential for cooling because we installed 342 kilowatts of our passive heat exchanger. So we can get most cooling out of the ground as possible, which means that we regenerate the ground as much as possible. So by putting as much cooling onto the ground, by injecting as much heat into the ground as possible, we lower the geothermal imbalance. So we have here 148 megawatt hours per year. In the previous situation, it was 170 megawatt hours. So the imbalance is now lower, which means that by using our 250 kilowatts, we can get up to 82% of the yearly share in geothermal heating and cooling. So if we compare that to our previous scenario, there it was 38 with 350 kilowatts. But here, with our 250 kilowatts, we see that we can get it all the way to the last year of operation. So we have 46% of our needed power is geothermal, and the other is for a hybrid system. And as you can see now, by using the optimized energy methods, we came to more or less the same conclusion as with the optimized power. Because now we do not have any oversizing in our heating system. If you recall that the total installed power was 536, you can see if we sum both up, we get that 536. So there is no oversizing in heating in this case. And we can get up to 78.2%. So if we compare that to our optimized power situation, here we only get 73%. And that's due to the difference in imbalance. So if we install more passive cooling in this case, and we correct for this imbalance, then we could install a little bit more geothermal heating to compensate for that effect. And that's basically what you see here in this case. So by installing more geothermal cooling, we have a lower ground imbalance. This means that the ground does not cool down as much as it did before, meaning that we can extract more heat from the ground. So that's basically how you play around really with this hybrid system design. By going to power and energy, optimizations and playing around manually with those maximum heating and cooling power, you can really get a feel on how your geothermal system behaves and how you can intelligently design your hybrid system, because now we have 250 kilowatts in heating. The previous case was 350, and here we got 83% of geothermal heating. So if you look at it from a total cost of ownership perspective, comparing investment cost with operational expenses, it will make a difference. And with GHEtool, you're able to calculate it really in detail and also export the power and the temperature to a CSV file to really grasp how everything works and what the ideal sizing would be for your case. I just want to mention one last thing, and that's that you have here the option to have a higher resolution. So now the results you got were on a monthly basis. If you switch it to an hourly profile, it will give you an hourly temperature profile in the end. But the important thing here to note is that the optimize energy methodology, as we've discussed in the previous video, it uses in the backend a monthly methodology, because otherwise it will take hours to calculate our optimal solution. So if you get the result from the hourly method, you will see that there are a little bit peaks that go over our temperature limits. So this is what you can see here. So on this lower resolution, you can see that there are peaks to 18 and even higher. But if we zoom in, you can see that the resolution betters. And if you really zoom in, you can see that, well, indeed, in some hours it goes to 17.4 degrees. And that's due to the methodology that is used, that it can produce peaks that are a little bit over the 18 degrees or 70 degrees your temperature limits. And with that final remark, I want to end this lecture. I hope everything was clear, and if it was not, perhaps check out also the other 2 articles in this series where we discuss more about what geothermal hybrid systems are, what geothermal potential is, and how both the methodology for optimized power and energy really work. Optimizing for energy and power, designing hybrid systems, it is a very complex and case-specific method. Depending on the space you have available, on your specific heating and cooling profile, depending on the amount of backup power or oversizing you want to do, depending on your economic parameters, you can end up with different designs. And that's an important thing to say, and I want to end with that in this tutorial, is that there is not one particular hybrid design that is the correct one. There are different choices that you can make. There are different correct ways to size, and with GHEtool, it's really easy to compare different options to each other, to check out what the maximum power is you can get. You can further optimize for energy, and you can really find the balance between the investment cost and the optimization cost. In the next part of this series, we will exactly do that. So for all the scenarios we've calculated here, we will make an economic comparison. So we will compare both the power we need to install, the investment cost for that. We need to take into account the operational cost of our different heat pumps over the whole simulation period. We need to take into account the amount of boreholes we need to drill. And that will give us a solution, let's say, or a final answer to which of the previously calculated scenarios is the right or the most correct one. If you found this video interesting, please check out GHEtool Cloud. Perhaps share this video with your colleagues as well, and subscribe to get informed when the new video comes out. I hope to see you there. Take care. Bye.